Hey scholars, I hope y'all are doing great today. We are about to start a new unit on similarity. Basically, we'll be solving problems with what we will call similar polygons. So today's going to be our intro lesson to this unit. Make sure you're taking good notes and paying close attention. Let's get going. So let's start off by asking this question. Which pair of triangles is similar? And why do we think so? Well, let's look at each pair of triangles. So, something that you might notice about this pair is that they look like they're a similar shape, but they're obviously different sizes. Here, they're obviously both triangles, but you can see that their angle measures are going to be different. This triangle number 3 definitely looks like a right triangle because we see that kind of L shape, so that looks like it's probably a right angle. Whereas the first triangle we see in both pairs, it may be an equilateral triangle, or at least it's close to looking like an equilateral triangle. We don't quite know for sure, but we can definitely tell that these are shaped differently, even though they're both triangles. But these appear to be the same shape, just different sizes. So we would call them similar triangles. One way to recognize that these are similar triangles is to think back on the transformations that we learned. Remember reflections, rotations, translations. We also learned about dilations. Now we would need to dilate these triangles to make them map onto one or the other. So we could look at number 1, triangle number 1, and we can dilate it, make it larger, and then translate it over, and it would match on to triangle number 2. Or we start with triangle number 2, shrink it, dilate it by making it smaller, and translate it to where it would fit onto triangle number 1. So if you can visualize those transformations, then you can get a good idea of whether polygons are going to be similar or not. So what we conclude, and you should get this in your notes, is that similar figures have the same shape, but not necessarily the same size. And two polygons are similar polygons if and only if they're corresponding angles, so they're matching angles, the ones in the same position, right? If their corresponding angles are congruent and their corresponding side lengths are proportional. So, get that again. If two polygons are similar polygons, if their corresponding angles are congruent and their corresponding side lengths are proportional. So, let's check this out. Let's look at these two similar figures. Okay? So, we see two right angles at A and D, and two right angles at E and H. And then we see a congruent angle at B and F. So angle B is congruent to angle F. And angle C, since they have two angle arcs, angle C is congruent to angle G. So you see that listed here. Angle A is congruent to angle E, angle B is congruent to angle F, angle C is congruent to angle G, angle D is congruent to angle H. So we know these are similar because their corresponding angles are congruent. So it checks that box. We have the congruent angles. And then their corresponding side lengths are proportional. Their matching side lengths are proportional. Let's talk about what that means. So AD, side AD is going to match up with side EH. Let's say this. Side AD corresponds to side EH. And check this out. Remember, angle A was congruent to angle E, so A and E, and then angle D was congruent to angle H, so D and H. They match up here in this ratio. All right, so now the length of AD is 5, and the length of EH is 10. So that simplifies to 1/2, doesn't it? 5 over 10 simplifies to 1/2. Now, let's look at another pair matching sides, corresponding sides. Side AB corresponds with side EF. So let's write that. We'll say AB over EF. All right, well, AB is 6 units. Say 6 over, and then EF is 12. So 6 over 12, which also simplifies to 1/2. So when we compare the corresponding sides, so AD corresponding to EH, AB corresponding to EF, and when we set them up as ratios, they will simplify to the same fraction. So that means that they are proportional. Now let's discuss this thing called the similarity ratio. Similarity ratio, and get this in your notes, is the ratio of the lengths of the corresponding sides of two similar polygons. So we actually just found the similarity ratio by comparing the smaller quadrilateral to the larger quadrilateral. We said AD, we were comparing AD and EH, and we said that simplified to 1/2, didn't we? All right, so we were comparing the smaller, one is smaller than 2, right? So we compared the smaller polygon to the larger polygon. Well, let's say we compared the larger polygon to the smaller polygon. So let's say we're going from the larger to the smaller. Well, let's just compare EH to AD this time. So EH is 10 and AD is 5. So 10 divided by 5 is 2. All right, so remember when we compared the smaller to larger, the similarity ratio was 1/2. But when we compared the larger to the smaller, the similarity ratio is 2. So here's what we're saying in this case. This polygon is half the size of the larger one. The larger polygon is twice the size as the smaller one. Okay? So we're just comparing the size of those similar polygons. So for this problem, we're asked to write a similarity statement for the two triangles, and then find the similarity ratio from the smaller to the larger, and then the larger to the smaller. Okay, so we didn't talk about a similarity statement yet, but let's check it out here. So I'm going to name this triangle QRS. Triangle QRS. QRS. And then we're going to say it's similar, so it's just one squiggle. Remember, if we said they were congruent, it's a equal sign with a squiggle on top, but for similar, it's just a squiggle. And now I'm going to compare the two triangles. So the other triangle, I need to figure out what is going to match up with Q. Well, we see that Q has two congruence arcs, doesn't it? Well, what has two congruence arcs over here? Oh, it's angle Y. So I'm going to start with Y because it has to correspond with Q. And then R has a single arc. Well, then Z also has a single arc. So Z is next because Z is in the because R is in the second place. Z has to be in the second place. And then we're just left with X, which has no arc, just as S has no arc. And they're both in the third spot. So remember, think back to when we did congruent statements. The corresponding parts had to match up. It's the same thing for similarity statements, okay? So now we want to find the similarity ratio from the smaller to the larger and the larger to the smaller. Well, the smaller to the larger, we're going to start here with triangle YZX. So all I need to do is I need to look at one of the sides. I'm just going to pick side XY. So XY. So I'm going to say XY, and X corresponds to S, and Y corresponds to Q. So we'll say XY over SQ. Well, XY is 6 units, SQ is 9 units, and if you simplify that fraction, 6 and 9 are both divisible by 3, so that'll simplify to 2/3. Now, you may have realized this earlier, but the ratio from the larger to smaller will be the reciprocal of the smaller to larger. So we said that the ratio from the smaller to larger polygon is going to be 2/3. Well, what's the reciprocal of 2/3? Think refliprocal. You just flip it over. It's going to be 3/2. Okay? So, what we're saying here is that the smaller to the larger, the smaller polygon is 2/3 of the size of the larger polygon, and the larger polygon is 3/2 the size of the smaller polygon. Okay? Or you could say 3/2 is 1 and 1/2. So that's how we write a similarity statement and how we find similarity ratios. Now the last thing we'll do is we'll learn how to find missing links in polygons. And we can use proportions to find the missing side lengths of polygons. That's how we're going to solve these problems. So check it out here. For number 1, we're going to find the value of m. So what we're going to do is use those proportional relationships that we just discussed. Let's think here. We know AD is 13, and WZ is going to be proportional to AD. Okay? But we don't have a length for WZ. We're not given that length, so that's probably not going to help us here. Now I am given the length of CD and the length of YZ, which are going to be corresponding sides of those polygons. So I can say that CD over YZ, and then that's going to be equal to BC, follow me here, which matches up with that side we're trying to find. We're trying to find M, right? And that M represents the length of that segment XY. So we can say this, CD over YZ will equal BC over XY. Something you need to pay close attention to is that if you're gonna have CD in the numerator, you need to have BC in the numerator as well, since they are on the same polygon. They're on the same polygon. CD and BC are on the same polygon. And then YZ and XY, they're on the same polygon, right? So we're putting them both in the denominator, okay? So now I'm going to substitute in for those values. Say CD is 10 and YZ is 15. And then BC is 12 and XY is M. Now one thing you can do, you do not have to do this, but it might help if you go ahead and simplify that fraction. So 10 over 15 simplifies to 2/3. So now think back to something you learned probably in about 6th grade. To solve a proportion, we need to cross multiply. So you multiply diagonally. So I'm going to say 2 times m, or 2m, equals 3 times 12. So 2 times m equals 3 times 12. Well, 2 times m is 2m. 3 times 12 is 36. And then we just divide both sides by 2. And we get m equals 18. So the length of m equals 18. We can say 18 units. M equals 18 units. So if that video was helpful for you, if you feel like it was confusing in any way, highly recommend rewatching certain parts. But make sure you're coming to class with questions and ready to learn. Good work today. Thank you, collegiate scholars.